Right, hi y'all. Today we're going to be going over, analog electronics and especially BJT DC analysis, what we're going to be doing in class this week. So I have this regular, transistor circuit here, and I want to find the current IC1 that is here. So we want to find current IC1. Okay. So the first thing that we should figure out here, and the one we're basically looking for, something we want to know beforehand, is what kind of transistor are we dealing with? Are we dealing with a PNP or an NPN? In our case, Q1 and Q2 are NPN transistors. Okay, so we are more focused on the forward active model, or the FAM. It is an amplifier. And what we want to figure out here is how can we um, model this in signals, or not signals, in a circuit model instead of having just a transistor. Now, you could, of course, solve it straight up, knowing the voltage drops and, solving it straight off with the circuit, but what our professor has said is use this forward amplifier model, or forward active mode model. And something else we're going to notice here is VBE is going to be equal to 0.7. And there was one more thing, I believe. Oh, beta. Yeah, beta is going to be equal to 100. So beta is 100. With this, you should be able to solve this. And one other thing we have to make sure and write down is the circuit model for this. So the circuit model for an NPN transistor looks like this. It's going to have a dependent current source, which is your IC. It's going to be equal to beta times IB, the base current. And remember, this is the collector. Then you have the base over here, and you have a voltage drop. Of course, this is the emitter. You have a voltage drop between base and emitter. And for an NPN, your VBE is positive 0.7. So you have a voltage drop of 0.7 volts, like this. And um, this is your NPN circuit model for forward active mode. And so now what we're going to be doing here is we're going to be redrawing the circuit in terms of our circuit model. So this is the circuit in the circuit model for our original transistor circuit. And here I've already labeled IC1, but there's some other voltages, or more like currents, that we'll need to make sure and label uh, to be able to use in our equations. So far, from what I've seen on the rubric for homework grading, and I assume exam grading for our analog electronics classes, if you use a variable in your equations, you have to have it labeled in your circuit. Of course, this goes back to Dr. Dave and your circuits 1 and 2 class, and even electronics. Make sure if you use any type of current or voltage in your equations, you have it labeled on your circuit diagram, your schematic. So here, we want to find IC1, and there are some other things that we could use here. There are equations for transistors, especially for NPN, is IC. I'm going to write the basic ones. IC is equal to beta IB. So if we want to find IC1, we need to find IB1. Well, where is IB1? IB1 is the current that flows from the base to the emitter in our circuit model. So if we look at the NPN here, this is IB. So for this here, IB1 will be here. It will not come after this line. It'll come before, on the left. And so what else do we know? Well, we know IB2. IB2 is here. That means we have, of course, we know there's a node here. That means there's a current flowing through here that I'll label IC1B1. Okay? This can become a little bit messy, especially if you have a lot of variables that you need to have initialized and put into equations, but this is what needs to be done. Okay, so knowing this, what else do we know? Well, we know IE is equal to, sorry, beta plus 1 IB1. Well, where's IE? Sorry, not IB1. IB. IE is the current. IE will be the current that flows out of the emitter. So for IE2, this would be IE2, and this would be IE1. The way they get this relationship is they do a KCL at this node, at the emitter node. And you notice, what is that? Well, it's 0 is equal to IE is leaving that node, IE1. What is entering that node? Well, IB1 is entering that node, and IC1 is entering that node. Let's use the relationship between IC1 and IB1. We can rewrite this equation as IE1. I'll put an arrow so we can now set this equal to. I'm going to move the IB1 to the left and IC1 to the left. But IC1 is equal to beta IB1. So now we can factor out an IB1, and this is 1 plus beta. So that's how they derive that relationship. So now, knowing that, these are the only two relationships you need to know to solve this circuit in particular. Now what we need to do is we need to create our KVLs and KCLs to solve this equation. So we want IC1. Well, there's one equation, or let's just, make some loops, first of all. Let's make some random loops here. So a loop would start at the ground there and go here. And what do we notice? Well, if we go here, then we can go here and go back all the way around because it's ground, right? Ground is ground. It's going to be connected somehow. We can't do that, really, because that would tell us that we need to find the voltage across this dependent current source. We do not want to deal with the voltages across current sources. So we're going to take advantage of the fact that we have this feedback loop here, the base collector feedback loop. So what we'll need to do now is, do you notice here, if we have a loop here, what can we do? Well, we can ignore that dependent current source. And then we go all the way back up, right? So we've ignored that dependent current source, and now we can find the voltages across everything else. Okay, so let's write an equation for that. And it's actually very important that we do this one because we're looking for IC1. And IC1 has a KCL at this node. So if we can find the current IE1, then it's one step closer to solving for IC1, because ultimately we need IB1. And of course, if we find IE1, we can use this relationship to find IB1, and then use that relationship to find IC1. I hope y'all can see the kind of pattern we're going here. Whenever you're solving these NPN transistor problems, it's a lot like a puzzle you have to solve. So here we go. So let's solve the KVL equation. Let me stop talking. So plus 20, but do we have a current initialized? Remember, if you use a variable in the equation, we need to have it in the schematic. So here, let's just initialize a random current. Let's say IN, whatever. I need that current, right? IN. So IN will be the current, and since it's going in the same direction as our loop, it's going to be positive. Then it becomes plus, following here, we get plus 0.7 plus 2.8 IE1. By the way, if you notice here, I don't put a K at the end of 20 because I'm going to assume my currents are in milliamps. So if you do this, know, and if you plug it into your calculator and you don't put the 1,000, know that your current will be milliamps at the end. It will not be in amps. So be careful about your units here, especially. But now we get to the bottom, it's minus 10. So now if we move everything over, we get 19.3 is equal to 20 IN plus 2.8 IE1. Okay, well, we have two unknowns. We have IE1 as an unknown and IN as an unknown. So we need another equation, at least one other equation. Well, what if we create a KCL at this node, the collector? This way, we have something in terms of IC1. Well, IC1 is in terms of IB1, and IB1 is something in terms of IE1. If we notice, we can start using these relationships to create equations that are not in our circuit. We can create equations that will eventually solve for the answer ourselves. You need to be able to know these relationships very well so you can see these sorts of things. So now what do we know about IN? Well, 0 is equal to, looking at this node, we have minus IN, and then we have plus IC1 B1. Remember, that's the current I initialized there, going out of the collector node into the base node, plus IC1. Well, again, we have another unknown here. We just introduced another unknown. We also introduced IC1, which we don't have. So again, we have to use our knowledge here. Use a KCL at this node now, at base 1. So 0 is equal to minus IC1B1, and IB2 is leaving, and IB1 is leaving. So what do we know about IC1B1? Well, this is equal to IB1 plus IB2. Okay, well that's something at least, right? Okay, well that's good. We can also say IN is equal to IC1B1 plus IC1. Okay, but what is IC1 equal to? IC1 is equal to beta IB1. Okay, so we're starting to put things together. Let's see if we plug this in. We get IN is equal to now IB1 plus IB2 plus beta IB1. This is starting to look familiar. Okay, look at this. We have a beta IB1 plus IB1. Well, that's IE1 using the relationship here. So now we can say IB2 plus IE1. Okay, now why am I doing this? Well, if we looked before here, we have IN plus IE1. Now what we have is, we still have two equations and two unknowns, but it's now in terms of the base and emitter currents. Usually for transistor problems, if you're not given any other initial currents, it's best to find equations in terms of your base collector and emitter currents. Because you have these very easy relationships, you can start putting things together very easily. Now, we have another problem here. Of course, we need to find the base current of the second transistor. So now we need to find another KVL. More than likely, we'll have to find another KVL to solve for the second base current. So let's do something very similar. Again, remember, you can't do this one because you can't do this loop because you're going, across, you're trying to find the voltage across a dependent current source. That's very hard. You don't want to do that. Let's start the same way we started with the initial loop. But instead of going left, let's go right. All right, so now you have this closed loop, and I'll put arrows to signify which way we're going. Okay. Now what we can do is we can create another KVL equation. Let's start here. 0 is equal to minus 10 plus 3. Oh, sorry, not 3. My bad. Plus 20 IN. And remember, we already have IN initialized as two collector and emitter or base and emitter currents. So now we do plus 0.7 because we go through the wire. Then we do plus 0.6 IE2. Oh no, so we've now brought in a new current. But what do we know about emitter currents? We can find them in terms of base currents. So now IE2, well not now, but we know IE2 is equal to what? Beta plus 1 IB2. And IN is equal to IB2 plus IE1. Well, that's really, really good for us because look, we found IE2 in terms of IB2, and IN has an IB2. So now it's getting very, very close. We're getting very close to the answer here. The next thing we need to do here is we need to first, let's simplify the green equation that we have here. And we get 19.3 is equal to 20 IB2 plus IE1. Or actually, we can change IE1 into beta plus 1 IB1 plus 0.6 beta plus 1 IB2. All right. So now, and just so y'all know, make sure I'm not confusing anyone, I plugged in 20. This is still IN. This comes from right here, and IE1, same thing as IE2, is equal to beta plus 1 IB1 now, right? And this is our IE2. But what do we notice about this equation here and this equation here? Well, they're both equal to 19.3. So if they're both equal to 19.3, we can set them equal to each other. So the blue equation at the top here, 19.3, is equal to 20 IN1. Well, IN1 is equal to IB2 plus beta plus 1 IB1 plus 2.8 IE1. IE1 is beta plus 1 IB1. And since they're both equal to 19.3, I don't have to have this 19.3 is equal to. I can set them equal to each other. So now we're going to do the green equation. 20 IB2 plus beta plus 1 IB1 plus 0.6 beta plus 1 IB2. So what do we notice? Well, what I notice at least, is this part and this part are identical. So we can cancel them out. Well, we can subtract them and move them over, right? Now what we have is 2.8, and beta is 100, so we can say 101 IB1 is equal to 0.6 times 101 IB2. So now we found a relationship between IB2 and IB1. Okay, so now what we can do is solve for one in terms of the other. So let's solve for IB2 is equal to, well, let's find this. So IB2 is going to be 2.8 divided by, 2.8 times 101 divided by 0.6 times 101. Okay, so I get about a 4.667 IB1. Well, we found a ratio between the two. Now what we can do, and I know this is kind of tedious here, but what we end up having to do here is we can now plug it back into either of the equations, the green or the blue, for IB2, and plug in for IB1, and solve for IB1, because now we have two equations and two unknowns. From here, you can plug it into your calculator. You should be able to solve for both. If you really wanted to, you could definitely do that. I'm not saying don't do that. But I don't have a calculator that can do that, so I'm just going to do this by hand here. So 19.3 is equal to 20 times IB2 is 4.67 IB1 plus 101 IB1 plus 0.6 101 times IB2, which is 4.667 IB1. Now 19.3 is going to be equal to something times IB1. And so now what we get is we get this. 19.3 is equal to 2,396.2202 IB1. And so what we end up finally getting is IB1 is equal to 8.054 times 10 to the minus 3. And remember what I said earlier. If you use not 20K, but just 20 for your resistance values, your final answer will be in milliamps. So IB1 is actually 8.054 microamps. But were we asked to solve for IB1? We were asked to solve for IC1. And the relationship between IC1 and IB1 is beta IB1 is equal to IC1, or 100 times 8.054 microamps. So what we get is 8.054 times 100 is 805.4 microamps, or 0.8054 milliamps. And that's how you would solve this equation using the NPN model, using a forward active mode circuit model. I recommend you use this mostly because knowing how to create these KVL and KCO equations and knowing which ones to use is very important, especially when you get into more complex circuit models. And especially in homeworks, especially with diodes, you have to worry about diodes and method of assumed states. That becomes very complex. I also recommend using LT-Spice or PSIM if you're in electromechanical energy conversion. I recommend using that a lot just to understand the idea of what these PNP transistors do and NPN transistors do. But anyways, this is how you would do this problem in BJT DC analysis. I'll definitely go over more problems with diodes and maybe not NPN transistors, but PNP transistors, and what happens whenever we deal with saturated or in cutoff regions of transistors. So hopefully this was helpful. If you have any questions, please comment down below. But yeah, I'll see you on the next one.